Okay guys, so today in class, hopefully you had a good first day. Basically what we've started talking about is one-dimensional motion. And when we talk about one-dimensional motion, essentially what we mean is that we have motion in a straight line. In other words, you can follow this linear path, you can go forward on it, you can go backwards on it, you can speed up, you can slow down, but the one thing you cannot do is turn off of that path. Okay, so for today we were definitely dealing with one-dimensional motion because today all of my motion occurred on this East Main Street, right? So for today I could move this way along the street, I could stop, I could move that way along the street, but one thing I could not do is turn off of East Main Street onto other streets, so this definitely qualifies as one-dimensional or straight line motion. Two other things I'd like you guys to know about motion in general is, first of all, it must always be described in a frame of reference. And in this case, we can consider this map to be our frame of reference. So a frame of reference, very simply, is what do we consider to be motionless so that we can compare our motion to it. And typically that frame of reference is going to be the surface of the earth like it is here. We consider the surface of the earth to be stationary and we compare our motion to the surface of the earth. But of course the surface of the earth is on a planet that is rotating, that is orbiting the sun, that is part of a solar system, that the universe is expanding, so it's not really stationary. We have to choose our frame of reference. Okay? Also, for my frame of reference, I chose to tilt my head a little bit to the side and pretend that this direction was kind of straight up and down. And so I called this the positive Y direction if I was going up that way. And I called this the negative Y if I was headed down in that direction. And then that makes these roads along here my x-axis. Okay? So if I was moving up in this direction, I called that the positive x direction, and this way I called the negative x direction. Now, that is not necessarily the correct way or the incorrect way. It was a way that was very easy for me, okay? And it was also a very typical way you might see someone do that. All right. Second thing we need to understand about motion is that motion must take place over time. Okay, we cannot travel from one point to another instantaneously. Motion always takes place over time. All right, so one of the first things I asked you to do today was to define 4 terms for me. And so here's one group's definitions right here, and they're pretty good ones, and we'll add some to that as well. And so for distance, what they've put there is how much ground an object has covered during its travel, okay? Which is very close to what I use for my definition. The definition I use for distance is the total length of path traveled, which is very, very similar definition there, okay? The other thing I want you guys to know is the standard units for distance, okay? And the standard unit for distance or displacement is the meter. All right, but how is distance different from displacement? So for displacement here, we have an object's overall change in position. Good, okay? Another way to define that is the straight line distance between the starting and finishing point. So the straight line distance between initial and final position along with the direction. Okay, it is important to understand that displacement also has a direction. And one technical way to explain the difference in those two is that distance is a scalar and that displacement is a vector. And so the big difference between those two terms is that a scalar is a magnitude only. So if I asked you how far you ran, you might say 5 kilometers. And that's a perfectly acceptable answer. Okay? But if I asked you what your displacement was while you were running, first of all, it may or may not be 5 kilometers. It will depend on the path you took. Second of all, if you did have a displacement, you would have to tell me the direction. So like I ended up 5 kilometers north of where I started. Okay? So distance is a scalar. It only has a magnitude, which means a value and a unit. But displacement is a vector, which means it has a magnitude and a direction. So it'll have a value and a unit and a direction. All right. For our other two terms, we have average speed and we have average velocity. Okay? And so average speed, the easiest way to define it is with the formula that they've written right there. The average speed can always be found by taking the distance, the length of the path you traveled, and dividing that by the time that it took to travel that path. And since distance is measured in meters and time is measured in seconds, we can measure our average speed in meters per second. But velocity is a little bit different. Okay? So for average velocity, that's actually going to be the change in position divided by the time, or another way to think of that is you take your displacement and you divide by the time. But once again, since displacement's in meters and time is in seconds, we have meters per second. So speed and velocity are very similar, but just like distance and displacement, speed is a scalar and velocity is a vector. And so speed is only going to have a magnitude, which means a value and units, such as meters per second. But a velocity is going to have a magnitude and a direction. Okay, so for the assignment today, there were basically 3 parts to my trip. And as you can see in the top picture there, one of the groups diagrammed my motion in this way. And so what I did was for the very first part, I started right here, and I decided to call this position x equals 0 meters. Okay? And then from there I went to the left, so my position's actually going to become negative from there. And if you see along the bottom picture, we have people measuring our scaled map with a ruler. I did something very similar. And so what I came up with was that this position right here where the blue arrow ends should be negative 152 meters. Okay? And we can go over the dimensional analysis for that and how I came up with that scale tomorrow in class if you guys have questions. Okay? Then for the second part of the trip, I had been walking at a pretty brisk pace on the first part. I turned around and I intentionally walked slower. And so what I found when I measured there was that this position right here at Garnett Street, okay, still on Main Street, okay, but that intersection should be x equals negative 116 meters. Okay? And then finally for the last part, I turned around and actually jogged back up to the intersection with what they've labeled here as South Alexander Street. And I found that my position for that point was negative 255 meters. All right. Second of all, we needed times for when I reached all those positions. Okay? And so I found that that first time that I turned around was at 1 minute and 57 seconds, which comes out to 117 seconds. The second time I turned around was at 2 minutes and 36 seconds, which comes out to 156 seconds. And then I found that I stopped at 3 minutes and 28 seconds. Okay? And if your positions are slightly off from mine and your times are slightly off from mine, that's fine. If we're completely different ballparks, then we'll need to get that straightened out tomorrow. Okay, so for my data table, I chose to have a trip 1, 2, 3, and then the total trip. I got the start time and the end time for each, and I got the initial position and the final position as each. Once again, I said that I started at 0 meters, and since all my other positions were left of that, you'll see that they're all negative values, because that's the sign convention that I chose to use. And sign convention just means, what does negative mean, what does positive mean? And in my case, negative means left, and positive means right, and that's a pretty traditional sign convention to use. Okay, so let's look at calculations here just for trip 1. Okay? And so if I wanted to know my distance traveled, I traveled in a straight path, so it's pretty simple. I walked from 0 to negative 152, so my distance traveled is just going to be 152 meters. Okay? Now, for my displacement, a very common symbol to use for displacement, and what we'll use in this class, is delta x. Okay? Because if x is my position, then delta x is my change in position, which is exactly what displacement stands for. Okay? And so delta anything is always final minus initial. So if I want to know for trip 1, my displacement, it's going to be my final position for trip 1 minus my initial position. So in this case then, it's just going to be negative 152 minus 0. And so of course then my displacement ends up being negative 152 meters. And so you'll notice that my distance and displacement are the same magnitude. They're both 152 meters. But what that negative does is tells me that this 152 meters is to the left. So another way I could write that delta x is 152 meters to the left. All right. Now speed is always distance over time. And so in this case, if I want to know the average speed just for the first part of the trip, I'm going to take my 152 meters and I'm going to divide that by my 117 seconds. And I came up with a speed for part 1 of the trip of about 1.30 meters per second. And my velocity is just displacement over time, so I'm going to say v equals delta x over t. And for that, since my delta x is negative, it's going to be negative 152 divided by 117, so that's actually just going to come out to negative 1.30 meters per second. So my distance and displacement are the same number, my speed and velocity are the same number, and sometimes that's true, sometimes that's not. Okay guys, I apologize. I just realized that I made a mistake on my final position here. So let's get rid of alright, and it also won't let me erase now, but this final position I wrote of negative 327 meters is not correct. Okay? That final position here should be negative 255 meters. Okay, so let's look now for our calculations for our whole trip. So if I'm doing my distance here, the only real way I can measure that length of path travel is I have to measure how far did I go to the left, and then how far did I go back to the right, and then how far did I go back to the left again, and I have to add together the absolute values of all of that. And so for the first part, I came out with 152 meters. And for the second part, I came up with 36 meters. And for the third part, I came up with 139 meters. And so I got that my total distance traveled was about 327 meters. Alright, so that is my distance. Now let's look at our displacement. There's two ways I could do the displacement. The easiest way to do it is just to do my final position and subtract my initial position. And so we said earlier that our final position was, so we take our negative 255 minus 0, and of course we get negative 255 meters, showing that at the very end of the trip I was 255 meters to the left of where I started on my diagram. Now, another way you could have done that is you could have taken the negative 152 meters we went for the first part of the trip and then added a positive 36 meters back to the right, and then had a negative 139 meters back to the left, and that should also come out to about negative 255 meters, or something very close to that. I think the two different ways of doing the measurements, my answers may come out slightly different there, but just about the same. Alright, so now let's look at our speed. So remember that our speed is just going to be our distance, total distance, divided by our total time. So our total distance for the trip was 327 meters, and our total time for the trip was 208 seconds. So if we take our 327 meters and divide it by our 208 seconds, you'll see that my average speed for the entire trip was 1.57 meters per second. But now let's look at our velocity. So our velocity is going to be our displacement, total displacement, divided by our total time. So in this case, that's going to be negative 255 meters divided by the 208 seconds. Okay? And so if I take my negative 255 and divide it by 208, I get a velocity of negative 1.23 meters per second, showing that for my whole trip, on average, I was moving 1.23 meters per second to the left. So you notice if you look at one leg of the trip, both the speed and the velocity are the same. You'll notice both the distance and the displacement are also the same number. Okay? But if you look for the whole trip, you'll notice that the distance and displacement are different numbers, and you'll notice that the speed and velocity are different numbers. Okay? And so there are times when they're the same, and there are times when they're not the same. And what I want you guys to think about is, when are those times? When are they the same, and when are they not the same? We'll talk about that in class tomorrow. Alright, so the last thing I wanted to talk about with this, because we'll be looking at this later this week, is some of you chose to do, in this case they called it displacement versus time. Typically we'd actually label that as position versus time. Okay, but the position versus time graph is a really important graph that we'll be talking about later this week. We'll also be talking about velocity versus time and acceleration versus time. But this is one graphical way to show the motion that I had. And the cool thing about this is that when you have a position versus time graph, you end up with these lines that have some slope, okay? And these slopes are important. So think about what those might mean, and we'll be talking about that later this week. Alright guys, I'll see you in class tomorrow. I hope that you come with questions. I didn't mean to answer them all here, but just to make sure you got what you were supposed to out of today's lesson. I enjoyed the first day of school, and I'll see you guys tomorrow.